Thank you all for coming. I'm going to be talking about recent work which we titled BBQ using AES and picnic signatures. This is going to appear at SAC this year. So it's joint work with Leuven, Emanuela and Nigel. And yeah, let's get started. So first I'm going to talk you through the couple of steps that we need to get to where we want to be. So I'm going to first explain how to do non-interactive zero-knowledge proofs using MPC-in-the-head with preprocessing. So there's a couple of big buzzwords, so we'll talk about each of them. Then I'm going to explain how picnic signatures work using MPC for binary circuits. And then I'm going to move on to our contribution, which is to use the AES block-cipher in an arithmetic circuit in the same context. And then I'm going to sort of show you what we estimate the comparisons would be between the sizes. And I'll motivate it a little bit later on when we get there. So quite a few buzzwords. So let's take each of them one at a time. So what do we want? Zero-knowledge proofs for arbitrary relation R, and we want it to be fairly efficient. So we have a public statement X, which is what we want to prove, and the prover has his private witness W that he doesn't want to reveal, obviously, but he wants to convince V that he has this witness. So in 2007, there was the great idea of using MPC, so multi-party computation, of the function which evaluates the relationship and evaluates to 1 if the relation holds true or 0 if it doesn't. And the idea here is that the prover is going to simulate the computation of the function in his head, and then he's going to present it to the verifier, and he's going to check that the MPC computation happened correctly. And this is what the proof is going to be. And so the security of the underlying MPC protocol guarantees first that the witness is not revealed because it's going to be shared across different parties, and also that the prover cannot cheat if he doesn't know it, because the computation of the protocol should not fail or should not return 1 if the witness is not a true witness. So how does MPC-in-the-head work? Well, we have this prover, this big prover box, and he's got W that he knows, and he has these 3 servers that he's going to simulate in his head. So he gives each of them a seed for randomness, and they're going to execute the multi-party computation, and he's going to sort of inject the witness into it. So not in the clear, obviously, but he's going to contribute the witness to the computation. And that's going to produce the evaluation of the function, which all the servers are going to learn. It's either going to be 0 or 1. And what does the prover get from it? Well, he gets 3 transcripts. So this is why you present your slides before, so you know that these things are happening. So these transcripts contain the seed of every server, and it's not very clear here, but it's got a share of the witness. So each server holds a random-looking piece of the witness that can be combined into the final witness, but not by any of them on their own. And they also have all the messages that the servers send to each other during the computation. And so we see here that the 3 pieces of the witness put together again create the true value. But even if 2 servers were to join together, it wouldn't be enough to find the real value. So this is how we're protecting the witness in some sense. So this is what the prover does. He does the MPC in his head. And how do we actually build a proof from that? So he's got these 3 transcripts, and it's going to be very much a Sigma protocol. So he's going to commit first to these transcripts, and then the verifier is going to say, well, I want to look at parties 1 and 3. So this is random every time. And then the prover is like, okay, sure, here is what party 1 and party 3 saw during the MPC execution. You can check them. So he's going to check a few things. He's going to check that the messages they sent to each other are consistent. He's going to check that none of them cheated. He's going to check that they both received the evaluation to be 1 at the end of the function. And this is how the check happens. So we can make this non-interactive in the usual sense. So the prover will hash his commitments to obtain the challenges of the parties that he has to include. And in the final message, he includes the 3 commitments at the beginning of the proof so that the verifier can recompute the hash and check that parties 1 and 3 were indeed the ones that had to be opened. So revealing only 2 out of the 3 transcripts is going to hide the witness, because you saw it was split into 3 pieces. And also the commitments means that the prover cannot change the randomness during the protocol to cheat, because if the messages don't match up with the randomness that was committed to at the beginning, the verifier is going to know what's up. Also, it could be that the prover could deviate actively from the MPC protocol. So he could actually make one of the parties change something and lie so that the evaluation forces to be 1. But first of all, he can only do this for 1 party, because the verifier is going to see the other 2 always. So he has to pick the right party to do this. So he can only have a success probability of 1/3 here. And actually in practice, it's not 1/3, it's like 1/64. So it's even smaller than that. And simply, like very common in proofs, we just repeat the proof in parallel with different random seeds every time, so that there's no leakage of the witness, but also the prover has a very low probability of cheating successfully on every proof. So just by repetition, we really lower the probability. So these are the properties of the MPC protocol that we use to guarantee the properties of the zero-knowledge proof. And also, there's a little trick that if you use broadcast, which means that, for example, server 2 doesn't send different messages to 1 and 3, he just sends the same message to everyone every time. Instead of revealing all of the messages from server 1 and server 2 and server 3, we can just include the messages that server 2 sends. So when the verifier gets the proof, it will contain the seeds of servers 1 and 3, so he can recompute all of their computation, because everything comes from the seeds. And it will also include the messages sent by server 2, because these are the only things he cannot recompute. And so this is how we kind of minimize what we have to send. So then the pre-processing part, that's because of the underlying MPC protocol. So some MPC protocols use pre-processing and online phase. The pre-processing is expensive but input independent, so it's just randomness and correlated randomness, whereas online is quite cheap but input dependent. So this can be used for the MPC in the head, but what we have to do is during the pre-processing phase, they're going to generate correlated randomness. So they're going to multiply 2 random values to obtain their product, for example. And the thing is, that product cannot be generated from seed. So a little bit of information has to be included to make sure. You will see in the examples later how this actually happens. But right now what you need to know is that on top of the seeds, we also need a little bit of additional information. But we don't need to include any of the pre-processing communication. So whatever expensive protocol you're using to compute these things, it doesn't matter in MPC in the head. So how would a full-scale proof work? The prover would first simulate and commit to the pre-processing execution. The verifier would challenge all except some of them to open and verify. And here it's very efficient, because since this is independent of the witness, the prover can reveal both the master seed, which is very short, and just the auxiliary information, which we're going to try to make as short as possible. And using only these 2 information, the verifier can verify an entire pre-processing execution. So it's very cheap in terms of proof size. With the executions that he did not open, the prover then does the online phase and commits to these ones. And as before, the verifier will challenge and verify that everything was executed correctly. Here it's 4 rounds. Well, it's 4 steps, but in practice we can squash this to make it non-interactive again. But I'm not going to give you those details. So what do we care? What we care about mostly is proof size in this context. Computation time is already very long for picnic signatures, so we're not really working on this one. And so we care about the size of the auxiliary information and the size of the communication in the online phase. So how does picnic signatures for MPC binary circuits work in this kind of thing. So the picnic signature scheme is a little strange because it's a public key primitive, it's a signature scheme, but it relies on symmetric key assumptions. So we have a block cipher F, and the key generation is that we pick a random plaintext block, a random key, we evaluate it to get the corresponding ciphertext block, and then the plaintext ciphertext pair is the public key of the signature scheme. And the secret key is the symmetric key that links them under the public key, under the block cipher, sorry. So the security of our key generation here is we're assuming that given the plaintext X and the target Y, it's hard to recover the key that links the two of them. So in some sense, it's a one-way function assumption. It's hard to recover the pre-image that maps the two. So even though it's a block cipher and you might assume, oh, it's a PRF from plaintext space to ciphertext space, no, it's a one-way function in this sense. Now the proof of knowledge we've been talking about is used in the signature algorithm, where we prove that the key is the one that maps X to Y. That's the relation we're trying to prove. And we include the message in the hash of the non-interactive transformation, as is standard for signature protocols. For the verification, it's just about verifying the proof, including the message to make sure that it was taken into account. And so Picnic chooses LowMC as their block cipher for efficiency reasons, because LowMC is a circuit that is specifically designed to reduce the number of AND gates, and you'll see why it's important. So it's designed to be MPC efficient. The other side, the flip side of that is that the LowMC circuit was only introduced in 2015, so there's not much security guarantees, not as much as AES. So this is where our work really originated. So how does it work for binary circuits? So we have F is represented with wires and gates, so we use XOR gates and AND gates. Every wire alpha has a real value, Z, masked, so as Z hat, so we XOR the Z with a mask lambda, and lambda is random for every value. Now this mask lambda is going to be secret shared. So every party is going to have lambda I, such that the sum of them is the real mask. And then every party is going to have the masked value Z hat and their share of the mask. So obviously every party alone cannot recover the real wire value, and even n-1 parties alone is still not enough to recover the entire value. So in idea, the pre-processing is going to prepare the masks that you need, and in the online phase, we're going to move from value to value until we get to the end. So in the pre-processing, we have a mask generated from seed for every input and AND gate output wire. For every XOR gate, the mask is easily computed as the XOR of the previous masks, so that's local and free. For the AND gate, it's a bit, because it's nonlinear, it's a bit more complicated. So we need this special value, which is the product of the two input masks. This is not free. Every party except for party N can set their share to be random from seed, so that's free in terms of pre-processing for us. But the last party has to make sure that his share agrees, so that when you sum all of them together again, you get the right product. So he cannot compute this from his seed. So the prover has to compute it from outside the MPC execution in some sense, and he has to include it in the auxiliary information. So this means that in this, we add to the proof 1 bit of information for every AND gate. We have to build the proof size, increase the proof size. In the online phase, if we want to reconstruct a mask, every party can just show their share. They're not lying, so that's fine. The parties will begin with the masks inputs and their masks from seed. And the computation proceeds just by computing every masked value in turn. For an XOR gate, again, it's local and free. You just XOR the two values and you get the result. But for the AND gate, you have to compute this value S, which requires this lambda alpha beta value that we pre-processed. And then they can open S, which is every party has to show 1 bit, and then they can recompute the output of the AND gate. So we need 1 bit per AND gate in the pre-processing, and in the online phase we need again 1 bit per AND gate to open the values. And this is kind of the baseline measure. So it's actually extremely efficient. Only a 2 bit per AND gate cost is very efficient. So the way the picnic signature scheme works is by combining the signature scheme from before and with this MPC protocol that I just went through. So as I said, you only need to open one seed. You need to open all the seeds except for one. And the message is sent by the last party that is not opened. So this is why we only have 1 bit of communication in the online phase for every gate. So this is a bit of a complicated looking formula, but to quickly run through it, kappa is the security parameter, so that's constant. T is the number of executions that is going to be run in parallel. Tau is the number of them that are going to be kept for the online phase, and N is the number of parties. So when we change the underlying MPC protocols, these all stay the same because they give the security guarantees of the signature of the proof and therefore the signature scheme. So this is how we estimate the size, and we see that it's really the size of the auxiliary information, the size of the key, but it's constant, and the size of the transcript that matter. All the other values are not going to change. So this is why I'm only really framing it in terms of for every execution you need so many bits for AND gates, so many bits in the online, because that's the easiest thing to change. So how do we move from a picnic to a barbecue? Well, you use a bigger piece of meat. And for us, that's going to be the AES algorithm. So most of you know it's a 128-bit state block cipher with key lengths of either 128, 192, or 256. The round function is 4 operations, and only one of them is nonlinear, so the sub-bytes, which was also known as the S-box. All the others use either XOR operations or just shifting some bytes around, so we don't need to worry about them too much. So the sub-bytes operation applies this inversion function over the field f2 to the 8. Unless the input is 0, in which case it just maps it to 0 itself. And then the public affine transformation, which is again easy, like it's again linear, so we don't need to worry too much about it. So the reason why we picked the AES block cipher is because, of course, it's standardized and it's been scrutinized for a lot more time than LOMC has. So, and it was actually mentioned in the NIST, when NIST selected the round 2 candidates, that picnic signature scheme was a great proposal, but that LOMC was a bit of an untested primitive, so they would like to see, for example, like estimates of how AES would do and these kind of things. And so, so this is why we really analyze this. So this is a very short slide to say that if you want to use binary AES, the best circuit out there at the moment takes 32 AND gates for every S-box. And you can see there's a lot of S-boxes in there, and I've got some estimates later that show you how bad that would be. Like the size would really be, the signature size would be very big. So this out of the box was not going to be good. So instead we moved to arithmetic circuits. So how do we do MPC for arithmetic? It's quite similar. Our function f is represented with values and plus and times gates, multiplication gates. Every value is shared, like before, like the masks were, so it's an additive sharing. But here we don't have a masked value, we just have the value itself is shared amongst the parties. So every party only has his share, and again, the pre-processing prepares the shared randomness and the correlated randomness, and in the online phase we're going to compute plus after plus, multiplication after multiplication. So operations with public constants are free. So if you need to add a public constant, multiply by a public constant, this is all local. And additions between shared values also, because we have a an additive sharing. And it's only the multiplication that costs pre-processing and communication, just like it was only the AND gates that cost us proof size before. If we assume that we have a triple, like here, where A, B are random and C is the product of them, then to do multiplication, we need to hide X and Y and open them in this sense. And then we have two field elements that need to be communicated. And then everybody can locally compute Z in this sense using this C value that is the product of A and B. So if we need to compute C in the preprocessing, again, we have a field element that needs to be added to the correlated randomness component of the proof. So in this context, it costs us three field elements to do a multiplication. One in the preprocessing and two in the online. So the thing is, for our AES circuit, we're not interested in multiplication so much, we're interested in inversion, because we have to do the inversion operation. So if we are given S as the S-box input, and a random R value, which is free, because it's generated from the seed again, first, the parties need to compute the product. So these are three field elements in terms of costs. Then they need to open this product, which is one more element of communication. And then they can locally invert this product and multiply back against their random value to open the shared inverted value. And that's it. So because this inversion operation is the only thing that we need to worry about for AES, we have a total of 32 bits per execution for every S-box. The binary circuit was 32 AND gates, and because it's 2 bits per AND gates, we have 64 bits required. So we have a theoretical 50% saving over just doing AES the naive binary way. Now we have a couple of issues here. Is that if R is 0 or S is 0, we have a problem because we rely on these inversion mechanics. So we have to avoid a few potholes on our way to our barbecue. So let's first do the R equals 0 one. If we assume S is non-zero, when we open the product, it will be equal to 0, so it's safe to assume that R was 0. So the protocol says that if this happens, you need to restart with a new random value, and it's very important that you restart with a new multiplication triple, because otherwise you can go back and reveal S. So that means because we commit to the triples in advance, it means we have to commit to enough triples at the beginning. Otherwise, we can't, during the online phase, suddenly say, oh, we need more triples, let's make more triples. That's possible for MPC in the real world, but in MPC in the head, you're fully committed to use only what you created at the beginning. So you have to make sure you have enough, because if you run out, you have to abort and restart your entire proof. Now, the good thing is that adding only 8 additional triples is enough for only 1 in every million proof to require an abort. So it's not that much material required, and you avoid. But I mean, if you're willing to take the risk, you can just not add any. And then your proof is slightly shorter, but you're restarting it more often. So it's a bit of a something you can parameterize. Now, the second pothole is when S is 0. And the problem is that S is input dependent, so we can't just resample, because if S is going to be 0 once, it's always going to be 0 for this execution. We could cover for it in secret, so you could add 1, invert 1 to 1, remove 1, so you're back at 0 again. But to do these tests in MPC in secret is quite expensive, and we cost that in our paper. But the most efficient solution is to make sure the problem doesn't happen. So at the beginning, when the key and the plaintext block are chosen, you just choose them so that there is no 0 input in any S-box in the evaluation of the circuit. It sounds like this would never happen, but for AES-128, this actually happens about 45% of the time, we can estimate. So it's not too hard to find such a thing. So the generation algorithm doesn't have to try, it can maybe try 2, maybe 3 combinations. It does reduce security a little bit, because remember, the problem is you're given X and Y, and you have to find the key that maps 1 to them. And if you're told that there's no 0 input to any S-box in the process, that is information that you can potentially exploit. But we estimate that this only reduces the concrete security by about 1.4 bits out of 128, so you're not breaking the whole thing. And actually, we can still formally reduce it to the PRF assumption. Because there is a non-negligible proportion of keys that satisfy this, the reduction still holds, and we're good to go. So now that we've covered these two problems, we can try and extend it to the L3 and L5 security levels. The problem is that the AES block cipher has a fixed block size. So when you're hashing a larger key, in some sense the one-way function is a larger key space, but still the same ciphertext space at the end. So the security of the assumption doesn't actually increase with the key size, because you get more than one key that match to the same plain text. So what we have to do is we have to use 2 copies of AES. So our number of S-boxes goes up, number of the proof size goes up, and we need slightly more additional triples. To get a bigger state, we combine them in ECB mode, which we truncate for AES-192. Now, people will say ECB mode is not a PRF. Of course it's not. But we can still show that we can reduce to the one-way CPA assumption on the ECB mode, which this holds. And so, of course, 2 copies of AES keyed with the same key. That's very important. And so again, the concrete security reduces to about 2.3 from 192 and 2.8 from 256. So we're really not losing much by picking our keys such that S equals 0 doesn't happen. Now the other way is to use the Reindel block cipher, because this one was actually designed to have bigger block size. So we can do this. We only need 1 copy of it. We don't need to combine it in any kind of mode. But because the state size is larger, the number of S-boxes still goes up. So here we have the number of X-boxes for Reindel. In brackets, we have the corresponding number of S-boxes for AES of the same key size. But the key schedule S-boxes are not doubled because we only need 1 key schedule since they're both keyed with the same key. So we see that for Reindel 192, we have less S-boxes because we double AES bluntly for 192, and then we truncate to match the 192 block size. So this is why Reindel is better adapted here, because it really only uses the S-boxes it needs for that kind of state size. But for 256, Reindel has a much bigger key schedule because you need to expand the key to a much wider state every round. And so in this case, AES has less S-boxes. But then the assumption is back again that Reindel is a PRF, which is again a bit more, has more confidence than LowMC, I would say. Even though focus has been on AES and not on Reindel. Because they're very similar, we could suppose that it's not any weaker. But this is perhaps still a question to think about. And again, the concrete security is reduced only a little bit because of our requirement for the S-box input. So finally, I can show you some estimates of how useful this all is to keep small proofs. So we have them divided by 3 level. The top lines are the binary circuits, the bold lines are our arithmetic inversion circuits, and the italics is the official, well, the picnic estimates. We compare them to the official picnic results, and they're very close to the averages that they obtain when they actually run them in practice. So this gives us confidence that our estimation method is pretty okay. So we see that every time we get a much better size than the binary, than the naive binary thing. So really, in this case, considering AES as an arithmetic circuit rather than the binary circuit really helps to save a lot of space. Of course, we don't do as well as Picnic because LowMC is really targeted to be efficient. And also it's very parameterizable, so they achieve the L3 and the L5 security level without needing to patch together 2 copies of it. So this costs us a bit. But already this is a much better step than doing it the naive way. And hopefully this will lead the research so that more tricks are found in order to interpret AES in a different way, to make sure, like to try and reduce the proof sizes even more so that we can use this really cool signature technique, but with block-cipher that gives us a bit more confidence. Any questions?